Welcome to Sleepless Scientist, the channel dedicated to exploring the mysteries of science in a way that soothes the mind and, hopefully, lulls you gently into rest. Here, we talk about the vast universe, the tiny atoms, the quiet revolutions of biology, and even the whispers of time, all delivered with care.com and just the right amount of nerdy joy. Tonight, let's take a journey into something strange yet intimately familiar: your sleeping brain. More specifically, the incredible process by which your brain continues to learn while you sleep. Yes, even as your limbs go still and your eyes close, your mind doesn't switch off. It turns inward. It replays, reorganizes, and rewires. Thank you for tuning in. And if this video makes your brain too excited to sleep, I apologize. Sometimes neurons can be a bit overzealous. If you enjoy this content, please consider liking the video, subscribing to the channel, and leaving a comment with your location and what time it is where you are watching. It's always fascinating to see how global our sleepless science community really is. Let's now settle in and dive deep into what your brain is really up to while you're dreaming of beaches, deadlines, or inexplicably being chased by spaghetti monsters. For a long time, sleep was considered a period of inertia, a time when the body and brain powered down like a machine on standby. It wasn't until the late 20th century that scientists began uncovering how dynamic and organized the sleeping brain actually is. One of the most surprising discoveries: sleep plays a pivotal role in learning and memory. In fact, it may be when the real work of learning actually happens. Throughout the day, your brain is bombarded with sensory input. It's a bustling office space of activity, processing conversations, storing facts, evaluating faces, sorting emotions, and occasionally wondering whether squirrels have a secret civilization. Each piece of information you encounter sparks activity in your neural networks, which are built from roughly 86 billion neurons. Neurons don't work alone. They form vast networks, firing electrical signals that help establish memories and skills. But during waking hours, these networks are volatile, noisy, and overwhelmed. When you sleep, that noise drops. Suddenly, there's silence in the office. Now, the overnight crew begins organizing the chaos. This is where sleep becomes a learning laboratory. Scientists have identified several key stages of sleep, but two in particular are central to learning: non-REM and REM sleep. Each stage contributes differently to the brain's nightly routine of cognitive housekeeping. During non-REM sleep, especially in the deep slow-wave stages, the brain exhibits large, synchronized waves of neural activity. It's during this time that your brain starts moving memories from the temporary storage of the hippocampus to the more permanent storage in the neocortex. Think of the hippocampus as a notebook you carry throughout the day, scribbling down observations. At night, the brain takes those notes and copies them neatly into a more stable archive. This is known as memory consolidation. Research using functional magnetic resonance imaging has shown that the hippocampus and neocortex often talk to each other during sleep. In fact, some experiments with rodents demonstrated that their brains replay sequences of neural firing patterns during sleep that mimic those experienced while awake. For example, a rat running a maze during the day will replay that same maze pattern while sleeping, almost like a ghost retracing its steps. This phenomenon is known as replay activity, and it suggests that the brain practices tasks even when the body is immobile. This memory replay isn't just a passive rerun. It's an active editing process. The brain filters through the day's events, discards what's irrelevant, strengthens what's important, and integrates new information with existing knowledge. It's like a librarian sorting a chaotic pile of books into a well-ordered shelf, sometimes discarding duplicates, sometimes finding hidden gems. Now let's talk about REM sleep. Rapid eye movement sleep, often associated with vivid dreams. This is when the brain becomes highly active again, exhibiting patterns similar to those of wakefulness. The prefrontal cortex, responsible for logical reasoning, becomes less active, which may explain why your dream logic often resembles a Salvador Dali painting. However, REM sleep is critical for emotional processing and creative problem-solving. One famous study from the University of California asked participants to solve puzzles involving word associations. Those who napped and entered REM sleep performed significantly better on the puzzles than those who stayed awake or napped without REM. It's as if the brain, freed from the rigidity of logic, starts to connect distant dots in novel ways. Creativity often relies on the brain's ability to find patterns and associations that are not immediately obvious. During REM sleep, brain regions like the amygdala and hippocampus become more active, suggesting an integration of memory with emotional tone. You might go to bed struggling with a dilemma, only to wake up with a fresh perspective. That's not magic. That's REM sleep hard at work, unconstrained by the bureaucratic oversight of the prefrontal cortex. The role of sleep in motor learning is equally compelling. Athletes, musicians, and gamers alike benefit from this. If you practice a physical skill during the day, like playing piano scales or perfecting a tennis serve, you'll likely perform better the next day after a good night's sleep. This improvement, even without additional practice, is attributed to neuroplasticity enhanced by sleep. Your brain is rehearsing movements, solidifying motor memory, even while your muscles lie still. In one experiment, participants were asked to tap a specific sequence on a keyboard as quickly and accurately as possible. After practicing the task, half of the group slept while the other half stayed awake. The next day, the sleepers showed a 20 to 30% improvement in speed and accuracy compared to those who had stayed awake. No extra training, just sleep. But what about the people who swear they don't need much sleep? Sleep deprivation. Studies offer some sobering results. Missing a single night of sleep can reduce your ability to form new memories by up to 40%. It's not just about being tired, it's about being cognitively compromised. Without sleep, the hippocampus becomes less effective at encoding experiences. Like trying to save a file without hitting the save button, chronic sleep restriction has longer-term consequences. In studies on medical interns and night shift, workers' sleep loss was associated with poorer recall, decreased focus, and reduced ability to solve complex problems. The brain isn't just tired, it's inefficient. If memory formation is like sculpting clay, sleep-deprived brains are trying to chisel through stone with a spoon. Let's also consider the role of brain waves in this entire process. Delta. Waves dominate during deep sleep, providing a restorative rhythm that supports memory transfer. Sleep spindles, brief bursts of high-frequency activity, have been linked to better retention of verbal and spatial information. Think of sleep spindles as brain fireworks lighting up neural circuits that have been newly wired through daytime experience. Children, with their developing brains, show more of these sleep spindles. This might be one reason why children can absorb languages, habits, and even social cues with astonishing speed. Their sleep architecture supports a supercharged kind of learning. Meanwhile, adults often struggle to pick up new skills, and declining sleep quality may be partly to blame. So, what happens when your sleep is fragmented? If you wake frequently or don't enter deep sleep phases, the consolidation process is disrupted. It's like trying to move a file to permanent storage while the power keeps cutting out. Memories become unstable, incomplete, or even lost. This is why students who cram all night might retain less than those who study and then sleep. To make it more fascinating, modern research is exploring whether we can enhance learning during sleep. In one curious experiment, researchers played sounds linked to specific memories while participants slept. When they woke, those memories were stronger than others. This hints at the possibility of targeted memory reactivation, although it's still in early stages. We're not quite at the point where you can play French lessons in your sleep and wake up fluent. But we're inching closer to understanding how memories can be selectively strengthened. The brain's ability to reorganize and solidify learning during sleep is nothing short of miraculous, and yet, most people view sleep as an inconvenience. The irony is that cutting sleep short in order to get ahead might actually undermine your progress. If learning is planting seeds, sleep is the sun and water that allows those seeds to grow. This is not just poetic metaphor, it's biology. In real time, happening every night beneath your skull, whether you notice it or not. As darkness settles over the landscape and your body slides into stillness, an astonishing transformation begins within the quiet confines of your skull. The brain, no longer burdened by external distractions, pivots inward. What emerges during this nocturnal state is not just rest but recalibration, an internal symposium of memory, learning, and self-repair that plays out across the grand theater of sleep architecture. One of the most intriguing questions in neuroscience is how different kinds of memories are handled during sleep. It turns out the brain isn't just passively storing away every experience like photos in a disorganized album. Instead, it's selective and strategic. Declarative memories, facts, names, and information you can consciously recall are largely processed during slow-wave sleep. Procedural memories, like how to ride a bike or solve a Rubik's Cube, often find refinement during REM and lighter sleep stages. Emotional memories, particularly those that carry a heavy weight, also receive special attention during REM sleep. To illustrate this, consider the experience of watching a sad movie or having an argument with someone close. The emotional charge of those events doesn't dissipate entirely while awake. Instead, REM sleep appears to strip the raw intensity from such memories, leaving behind a calmer narrative. Researchers have described this as sleep to remember, sleep to forget. The notion that sleep preserves the memory itself while easing the sting. This might be why heartbreak often feels slightly less unbearable after a good night's sleep, even if nothing has changed externally. Neuroscientists have used polysomnography, a comprehensive recording of the biophysiological changes that occur during sleep, to analyze these processes in meticulous detail. Electrodes placed on the scalp can measure the exact moment when the brain transitions between sleep stages. The sequence is consistent, drifting through light sleep, sinking into deep slow-wave sleep, and finally climbing into REM sleep before the cycle repeats. Each cycle lasts about 90 minutes and occurs 4 to 6 times per night. However, the proportion of deep sleep versus REM shifts throughout the night. In the first half, deep sleep dominates, prioritizing memory consolidation and physical repair. In the second half, REM sleep becomes more prevalent, enabling creativity, emotional processing, and cognitive flexibility. It's as though the brain saves the abstract, dreamy work for the final acts of the night. Among the many microscopic actors in this neural drama are synapses, the tiny gaps between neurons through which signals pass. During the day, new connections are formed as you encounter new information, forming what neuroscientists call synaptic potentiation. However, too much synaptic activity leads to a saturation point, like a hard drive nearing capacity. During sleep, the brain undergoes a phenomenon called synaptic downscaling. It trims away the weaker or redundant connections, preserving only those that are meaningful and efficient. It's spring cleaning for the nervous system. This process not only maintains cognitive clarity, but also prepares the brain for learning. The next day, without this nightly pruning, the brain would become overwhelmed, foggy, and less adaptable. It's a bit like trying to build a sandcastle on top of an old, crumbling one. You need to flatten the ground before you can start anew. Sleep does that leveling, allowing each day to begin with a refreshed mind. The idea that learning continues during sleep has long captivated scientists and dreamers alike. In recent years, experiments have taken the bold step of trying to enhance learning through subtle interventions during sleep. One method involves pairing specific sounds or scents with newly learned material during wakefulness, then reintroducing those cues during slow-wave sleep. The results have shown modest improvements in recall, suggesting that the brain can indeed be nudged to prioritize certain memories. This isn't quite sleep learning in the sci-fi sense, but it hints at a future where education might one day stretch beyond waking hours. There's also growing interest in how dreams themselves reflect learning. While dreams remain elusive and mysterious, some studies suggest they are an outgrowth of memory consolidation. The theory goes like this: as the brain replays and reorganizes information, fragments of that data sometimes coalesce into the strange, narrative-like sequences we call dreams. That time you dreamed about taking an algebra test on the moon while eating pancakes. Your brain may have been integrating math anxiety, space documentaries, and breakfast cravings, not necessarily in that order. Some psychologists argue that dreams function as virtual simulations. They provide a safe space to rehearse social scenarios, threats, or personal dilemmas without real-world consequences. The amygdala, a brain structure involved in fear processing, is notably active during REM sleep, adding emotional coloring to these internal simulations. It's possible that through dreaming, we explore variations of reality, expanding our behavioral repertoire in preparation for real-world situations. This might explain why dreams often contain elements of learning, problem-solving, or social rehearsal. Anecdotal reports abound of musicians composing melodies in dreams, scientists solving equations, or novelists crafting plot twists. The brain, relieved of sensory interference, may freely associate, rearrange, and invent. It's not always productive. Sometimes it's just flying zebras and talking furniture, but the potential for creative breakthroughs is undeniable. While this nocturnal creativity fascinates, the consequences of its absence can be severe. Sleep disorders like insomnia, sleep apnea, and restless leg syndrome don't just disrupt rest. They interfere with the brain's ability to encode and consolidate memories. In people with untreated sleep apnea, for instance, the oxygen supply to the brain is frequently interrupted, leading to cognitive decline over time. Studies have shown that memory, attention, and executive function all deteriorate when deep and REM sleep are repeatedly fragmented. Even healthy individuals experience temporary cognitive deficits after sleep restriction. One study found that people who slept only 4 hours a night for 6 consecutive nights performed tasks with the same impairment level as someone legally intoxicated. Yet participants reported feeling fine, unaware of how deeply their cognition had slipped. This mismatch between subjective alertness and actual performance is dangerous, especially for people operating vehicles, machinery, or, say, performing surgery. To maintain optimal learning and memory function, scientists recommend a sleep duration of 7 to 9 hours per night for adults. Teenagers, whose brains are still in developmental overdrive, require even more, typically 8 to 10 hours. Yet, cultural habits often push against these biological needs. The glorification of late-night productivity and early rising has created a sleep-deprived society that may be undermining its own intelligence. The irony is sharp. In our quest to learn more, achieve more, and do more, we sacrifice the very process that enables deep learning. It's akin to burning the instruction manual in order to assemble the machine faster. Sleep's relationship with learning extends even further into neuroplasticity, the brain's ability to adapt and change over time. In children, whose brains are incredibly malleable, sleep supports the rapid acquisition of language, motor skills, and emotional regulation. But adults are not static either. When adults learn a new skill, whether it's painting, speaking Italian, or mastering the ancient art of sourdough baking, their brains must rewire. Sleep facilitates this. Rewiring. Magnetic resonance imaging has shown that areas of the brain activated during learning light up again during subsequent sleep. It's like a rehearsal without conscious awareness. This neuroplastic rehearsal allows the learned behavior to move from clumsy and deliberate to smooth and automatic. In essence, sleep is the final training ground before performance. In neurodegenerative conditions like Alzheimer's disease, disrupted sleep patterns often precede memory loss. This has led researchers to explore whether improving sleep might delay the onset or progression of cognitive decline. Some findings suggest that sleep helps clear amyloid beta, a protein linked to Alzheimer's, from the brain. If true, this places sleep not only at the center of learning, but also as a potential shield against forgetting. In light of all this, it's worth rethinking the common phrase, "sleep on it." What was once colloquial wisdom now carries scientific weight. Whether you're grappling with a difficult decision, preparing for a presentation, or trying to absorb a textbook's worth of information, sleeping on it might be the most intelligent move. The brain is not a passive recipient of learning, and neither is sleep a passive state. The two form an elegant, reciprocal dance. Daytime experiences are processed during sleep, and quality sleep enhances the ability to learn again tomorrow. It's a cycle of renewal, refinement, and reinforcement, repeated night after night in silent darkness. And while the world spins on, unaware of what takes place behind closed eyelids, your brain is diligently at work, refining your memories, sharpening your skills, and making sense of the chaos you encountered while awake. While the conscious mind retreats into the folds of darkness and dreams, the brain does not simply lie dormant. It shifts roles from outwardly focused receiver to inwardly orchestrated conductor, presiding over a symphony of neurons rehearsing, refining, and rerouting the tunes of memory and learning. This nightly performance is not random nor leisurely. It is methodical, intensive, and strangely poetic. Sleep is not the absence of consciousness, but a different kind of awareness. A hidden laboratory of thought. Delving deeper into the neurobiology of sleep, learning brings us to the hippocampus, a seahorse-shaped structure buried within the medial temporal lobe. Often dubbed the brain's event recorder, the hippocampus excels at logging information gathered throughout the day. When you remember where you parked your car or recall the name of a new acquaintance, you're using your hippocampus. However, it isn't a warehouse. It's more like a relay station, temporarily holding data before passing it to the neocortex, where long-term memories are stored. This transfer process intensifies during slow-wave sleep, the deep, dreamless state characterized by low-frequency brainwaves and reduced heart rate. In this stage, the hippocampus and neocortex engage in rhythmic communication. It is during these pulses of synchronization that memories are most actively consolidated. Sleep spindles, those brief bursts of activity detected on an EEG, often align with these pulses, facilitating the migration of information. Like trucks on a night shift, they ferry memories from the hippocampus to their long-term destinations. What's particularly fascinating is the precision of this transport. Not every memory is granted a ticket. The brain sifts through the day's events, tagging some for preservation and others for deletion. Emotional intensity, repetition, novelty, and relevance to existing knowledge all increase the chances of a memory surviving the cut. If you watched a thrilling documentary about volcanoes right after an uneventful commute, chances are your brain will choose the eruption over the traffic lights. This selectivity highlights one of the most compelling aspects of sleep-based learning. It is efficient. The brain doesn't waste resources encoding everything equally. It makes executive decisions, quiet, nocturnal choices about what is worth keeping. This process is so vital that experimental disruptions to slow-wave sleep have resulted in measurable impairments in memory retention, even after just one night. But memory isn't simply stored like a photograph in a drawer.
Sleep doesn't
Just protect memories. it transforms them. Raw experiences are restructured, recontextualized, and sometimes even enhanced. If learning while awake is about laying bricks, then sleeping is about arranging those bricks into meaningful architecture. This remodeling is particularly crucial for what scientists call gist extraction. Rather than recalling exact details, the brain during sleep tends to distill the core message. For instance, you may not remember the exact words of an article you read, but you retain its main idea. This abstraction allows for generalization, the brain's ability to apply learned knowledge to new situations. Consider language acquisition. Children learning to speak not only memorize words, but infer grammatical rules through repetition and variation. Sleep helps consolidate these implicit patterns. Studies show that toddlers who nap after hearing a new verb structure are more likely to apply it correctly later. Without sleep, the brain struggles to detect and apply patterns. It's like trying to guess the rules of a board game while constantly forgetting the previous rounds. Sleep doesn't merely sharpen individual facts, it fosters understanding. In a study involving transitive inference, understanding that if a greater than B and B greater than C, then a greater than C, participants were better at drawing the correct conclusion after a night of sleep than after an equal period of wakefulness. This suggests that sleep promotes inferential reasoning, connecting fragments into coherent wholes. Essentially, the brain isn't just remembering, it's thinking. This thinking becomes even more dynamic during REM sleep, where brainwave patterns resemble those of waking consciousness, yet with crucial differences. The prefrontal cortex, associated with decision-making and inhibition, becomes less active, while the limbic system, responsible for emotions, lights up like a fireworks display. This unique configuration allows for what scientists call hyperassociativity, the ability to form connections between unrelated ideas. It's no coincidence that many artists, scientists, and thinkers throughout history have credited sleep with breakthroughs. The chemist August Kekulé famously dreamt of a snake biting its own tail, inspiring the ring structure of benzene. Mary Shelley claimed the idea for Frankenstein came from a dream. Paul McCartney reportedly composed the melody of Yesterday in his sleep. These anecdotes, while romanticized, align with what neuroscientists now understand. REM sleep is fertile ground for creativity. Dreaming, though difficult to measure scientifically, may serve as a testing ground for these novel associations. As the brain spins stories using fragments of memory, it stretches the boundaries of conventional thinking. These dream scenarios, bizarre, whimsical, sometimes unsettling, may help the brain simulate complex emotional situations or practice decision-making in abstract ways. It's like sandbox mode for the mind. Some researchers hypothesize that this narrative weaving serves to emotionally process difficult events. Traumatic memories, particularly, are revisited during REM sleep, possibly as a way of gradually reducing their psychological sting. This could explain why people with PTSD often suffer from disturbed REM sleep. Their brains are stuck in a feedback loop, unable to process the trauma to completion. The interplay between memory, emotion, and dreams is evident in the amygdalas. Role during sleep. This almond-shaped cluster of neurons, deeply embedded in the temporal lobe, acts as the brain's alarm system. During REM, it becomes unusually active, likely contributing to the emotional vividness of dreams. Yet paradoxically, REM also seems to help regulate these emotions. The emotional brain is firing intensely, but the logical overseer is offline. It's emotional storytelling without editorial review. Back on the more structured side of sleep, we return to non-REM stages, especially stage 2, where sleep spindles dominate. These spindles appear to play a role in protecting sleep from external noise while also aiding memory. Some studies have shown that individuals with more frequent or denser sleep spindles tend to score higher on IQ tests and memory tasks. While it's not a direct correlation, it hints at the importance of these subtle bursts of brain activity. In older adults, sleep spindles and slow-wave activity tend to decrease. This decline is associated with memory complaints and cognitive decline, underscoring the importance of maintaining healthy sleep as we age. Efforts to enhance slow-wave sleep through auditory stimulation, such as playing pink noise synchronized with brain rhythms, have shown promise in improving memory in older participants. The pursuit of understanding how to support sleep for optimal learning has also sparked interest in sleep hygiene, the set of behaviors and environmental conditions that promote high-quality rest. Things like maintaining a regular bedtime, minimizing screen exposure before sleep, reducing caffeine intake, and ensuring a dark, quiet room have been shown to increase time spent in slow-wave and REM sleep. These practical steps aren't glamorous, but they're scientifically supported and surprisingly powerful. Then there's the question of naps. Can short bursts of sleep offer the same learning benefits as a full night? The answer depends on the type of memory. Studies have shown that even a 90-minute nap that includes both non-REM and REM stages can enhance perceptual learning and memory consolidation. Students, athletes, and shift workers can all benefit from strategic napping. However, naps are supplements, not substitutes. The full cycle of overnight sleep remains the gold standard for brain maintenance. Another rising frontier is the concept of lucid dreaming, where a person becomes aware that they're dreaming and can sometimes influence the dream's content. While still niche, early research suggests that lucid dreaming might offer opportunities for deliberate mental rehearsal. Some dreamers report practicing musical instruments, speeches, or sports within their dreams, with some reporting improvements in performance afterward. Whether these effects are placebo or truly neurological is still being explored. Even more experimental are brain-computer interfaces designed to detect sleep stages in real time and deliver subtle inputs to enhance learning. These might include auditory cues, smells, or gentle vibrations timed to specific sleep phases. While most of this research is still in early stages, it speaks to a broader recognition. The brain remains exquisitely active while the body sleeps, and perhaps, with care, we can harmonize with that activity to foster growth. It's important, though, to avoid turning sleep into another productivity metric. Sleep is not a means to an end, but a vital process in itself. Its contributions to memory, learning, creativity, and emotional regulation are deeply intertwined with our humanity. In trying to optimize it, we must not forget to respect it. There is a quiet intelligence in the cycles of sleep, an intelligence not of words or reason, but of rhythm, chemistry, and cellular choreography. As the stars move across the sky and eyelids flicker in dream, the brain continues its labor of sculpting the self, shaping knowledge, feelings, and imagination into something coherent. It is a silent endeavor, ancient and ongoing, and we owe much of who we are to what happens when we are unaware. As the night deepens and the world outside fades into stillness, the brain enters a phase of refinement and prioritization. This is no passive drift. Within your skull, nearly 86 billion neurons engage in a synchronized choreography, delicately sorting, stabilizing, and pruning the raw material of your daily experience. Sleep is the sculptor's hand, etching fine details into the brain's living architecture, turning impressions into knowledge and encounters into understanding. A key mechanism in this nightly transformation is synaptic plasticity, the ability of neural connections to strengthen or weaken over time based on activity. During waking hours, your brain is in a mode of synaptic potentiation. Connections between neurons are reinforced as you learn, practice, and interact. But as you accumulate new information, the neural landscape becomes saturated. Synapses can't continue to strengthen indefinitely. Sleep provides the reset. It's during this offline state that synaptic downscaling occurs, allowing the brain to balance energy consumption, enhance signal clarity, and refine memory networks. In this quiet process, the strong connections, those repeatedly activated by meaningful experience, are retained or strengthened further, while weaker, redundant ones are trimmed. This selective pruning doesn't just preserve memory, but sharpens it. It enhances signal-to-noise ratio across the brain's information networks. Think of it like a gardener trimming back a tree, not to reduce it, but to help it grow with more direction and efficiency. During deep non-REM sleep, bursts of delta waves ripple through the cortex, and this is when synaptic recalibration is most robust. Sleep spindles continue their flickering dance across the brain, and paired with slow oscillations, they orchestrate the transfer of memory from temporary storage in the hippocampus to more durable representation in the neocortex. This interregional dialogue is crucial. Without it, memories remain fragile and inaccessible. But sleep's contributions extend far beyond rote memory. It also promotes insight. Insight can be thought of as a sudden reorganization of information. A shift in understanding, the proverbial light bulb flickering on. Researchers studying problem-solving tasks have found that sleep enhances the ability to discover hidden rules and patterns. In one experiment, participants were given numerical puzzles with a concealed shortcut solution. Those who slept after the training session were more than twice as likely to figure out the shortcut compared to those who stayed awake. Sleep allowed their brains to connect dots in ways conscious thought had not. This ability to abstract and reorganize is not limited to puzzles or equations. It manifests in our daily lives in the ways we reflect on relationships, reassess decisions, and reinterpret past experiences. Dreams may even play a role here. While often chaotic and illogical on the surface, dreams weave together recent memories, distant recollections, and emotional residues into narratives that occasionally illuminate, inspire, or warn. The dream state can act as a testing ground, a mental space where the brain runs simulations without real-world stakes. You might dream about a job interview, a confrontation with a friend, or a triumph on stage. These aren't simply random projections. They might be your brain rehearsing, refining responses, or framing possible outcomes. By integrating new information with old frameworks, dreams can offer emotional rehearsal and social problem-solving in abstract form. Neuroscientists believe that REM sleep, in particular, is responsible for this mental theater. With its high brain activity, irregular breathing, and rapid eye movement, REM is where the most vivid dreams occur. It's also where emotional experiences are reprocessed. The amygdala, associated with fear and strong emotion, becomes more active, while the prefrontal cortex, the seat of logic and judgment, dials down. This allows emotionally charged memories to be revisited in a safe context, without the anxiety they might provoke during waking life. This has profound implications for emotional learning. For example, exposure therapy, used to treat phobias and PTSD, is more effective when followed by quality REM sleep. The sleep period after the therapy appears to consolidate the new, less fearful association, reducing the emotional charge. Similarly, people who sleep after viewing emotionally disturbing images rate them as less intense the next day, compared to those who remain awake. Sleep, it seems, doesn't just help us remember. It helps us move on. On a neurochemical level, sleep stages feature distinct cocktails of brain chemicals. Non-REM sleep involves a reduction in norepinephrine and acetylcholine, fostering slow-wave patterns ideal for memory transfer. REM sleep, by contrast, includes bursts of acetylcholine with little norepinephrine, creating a brain state that is simultaneously alert and emotionally vivid. This neurochemical environment supports not just memory processing but creativity, the ability to generate novel ideas and associations. There's also an intriguing role of sleep in learning motor sequences. Skills like typing, playing an instrument, or even brushing teeth with your non-dominant hand all rely on procedural memory. These are reinforced during stage 2 sleep and REM in experiments. Subjects trained on specific finger-tapping sequences performed better after a full night of sleep than those tested immediately after practice. This suggests that the body rests while the brain continues to rehearse. The timing of sleep can also affect learning outcomes. A nap shortly after acquiring new knowledge can provide many of the same memory benefits as a full night's sleep, especially if the nap includes both non-REM and REM phases. In one study, participants who napped for 90 minutes after learning word pairs performed significantly better on recall tests compared to those who stayed awake. The timing and quality of sleep seem to be just as important as duration. Interestingly, the process of memory consolidation during sleep is not confined to humans. Songbirds replay their songs while sleeping, likely refining their vocal patterns. Rats rehearse mazes. Zebrafinches refine their chirps. Across the animal kingdom, sleep appears to support learning in various forms, hinting at a deeply conserved evolutionary function. Sleep is not a luxury. It is a biological necessity for intelligent life. But what happens when this process goes awry? Disrupted sleep, whether from insomnia, stress, or environmental factors, interferes with the continuity of memory processing. Fragmented sleep reduces the duration and intensity of slow-wave and REM phases. This weakens the consolidation of both factual and emotional memories. People with fragmented sleep patterns often experience cognitive sluggishness, mood instability, and difficulty integrating new information. In more extreme cases, chronic sleep deprivation has been linked to increased risks of neurodegenerative diseases. Research indicates that the brain's glymphatic system, responsible for clearing metabolic waste, operates most efficiently during deep sleep. This includes the removal of beta amyloid, a substance associated with Alzheimer's disease. Sleep may therefore hinder the brain's cleaning mechanisms, allowing harmful proteins to accumulate over time. The glymphatic system acts like a plumbing network for the brain. During sleep, cerebrospinal fluid flows more freely between brain cells, flushing out waste. This fluid movement is reduced during wakefulness, but surges in slow-wave sleep. It is during this time that the brain's metabolic housecleaning occurs, ensuring that the circuits involved in memory and learning are not clogged with debris. Protecting sleep, then, is not merely a matter of avoiding fatigue. It's about safeguarding cognitive health, emotional balance, and long-term brain function. Strategies to improve sleep, regular schedules, screen reduction, ambient noise control, and mindfulness are therefore not just lifestyle hacks. They are neural investments. Emerging technologies are also beginning to target sleep directly. Wearable devices can now track sleep cycles with remarkable accuracy. Some are even designed to nudge the brain toward specific phases by delivering gentle sounds or vibrations at opportune moments, though still in early stages. These interventions reflect a growing recognition of sleep as an active partner in the learning process. Looking ahead, researchers are also investigating pharmacological tools to enhance slow-wave sleep or prolong REM duration. While the ethical and safety implications are still being debated, the goal is clear: to harness the sleeping brain's potential in more targeted and effective ways. And yet, despite all this scientific insight, the essential mystery of sleep remains. Why does consciousness yield so completely? Why must the brain retreat in order to learn? What evolutionary pressures shaped such a peculiar strategy? What we do know is this: while the external world pauses each night, an internal world awakens. And in that world, your brain is busy, crafting new skills, healing old wounds, rehearsing future possibilities, and quietly weaving the threads of a smarter, wiser self. Deep within the quiet hours of the night, while the body rests motionless and unaware, the brain works with quiet urgency. It disassembles fragments of the day, evaluates memories, rebuilds patterns, and integrates information into the architecture of long-term knowledge. This subterranean cognitive labor is not optional. Without it, the brain begins to stumble. With it, the mind becomes more adaptable, more intelligent, and surprisingly resilient. Sleep, far from being an idle interval between waking states, is a form of active learning. The brain does not simply replay daytime memories in perfect fidelity. It edits them. It cross-references them. It sometimes even upgrades them, infusing ordinary experiences with contextual relevance or emotional resonance that was not present during wakefulness. This process, invisible to our conscious perception, is central to how we become who we are. One of the most fascinating examples of this invisible transformation comes from studies of learning sequences. The ability to process and remember a series of events or steps. A common experimental design involves participants learning a string of movements, such as pressing keys in a specific order on a keyboard. After a night of sleep, performance on the task typically improves. But the enhancement is not simply in speed or accuracy, it's in fluency. The motions become smoother, less conscious, and more natural, as if the body has internalized the rhythm. This kind of procedural learning relies heavily on specific stages of sleep, particularly non-REM. Stage 2 and REM sleep. Stage 2 sleep is characterized by the presence of sleep spindles, which are believed to coordinate activity between the thalamus and the cortex. These coordinated bursts of activity are associated with the reinforcement of motor sequences and PESK, and visual patterns acting like neural glue that binds discrete moments into coherent actions. Even more impressive is the brain's capacity to integrate abstract information across contexts during sleep. In one study, participants learned a series of overlapping associations. For example, A is paired with B, and B is paired with C. After sleep, many participants were able to infer that a must also relate to C, even though they were never explicitly taught this connection. This is transitive inference, a cornerstone of logical thinking, and it was enhanced simply by sleeping. Such findings suggest that sleep does not merely preserve memories, but actively constructs mental models. It strengthens associations, identifies patterns, and even generates predictions. The brain is not just remembering, but understanding. This difference between memorizing and internalizing may be why cramming for an exam and then staying awake all night is far less effective than studying well and sleeping soundly. Sleep also appears to support what's called relational memory, the ability to link together pieces of information that may not be obviously related. Imagine you're introduced to a new person at work and later see them walking a dog in the park. Sleep helps the brain weave those moments into a single narrative. You may not consciously realize it, but the next time you see the dog, you're likely to remember the person, their name, and perhaps even the office where they work. This capacity to form networks of meaning is a cornerstone of flexible intelligence. Emotional learning, too, is profoundly shaped by sleep. Emotions are not neatly filed away like names or dates. They are embedded in memories, decisions, and behaviors. REM sleep appears especially crucial in rebalancing emotional tone. In sleep laboratories, people exposed to emotionally provocative images show diminished reactivity to those images after REM sleep. Brain scans reveal less activation in the amygdala and more in the medial prefrontal cortex, a shift from emotional alarm to rational appraisal. This nocturnal emotional processing helps regulate mood and resilience. Individuals with disrupted REM sleep often report higher levels of anxiety, irritability, and even depression. In fact, irregularities in REM sleep architecture have been observed in many mood disorders, suggesting that this stage of sleep plays a protective role in mental health. Even dreams, as perplexing as they may be, seem to serve a function beyond mere entertainment. While not all dreams are memorable, and many seem absurd, they often involve emotionally charged or socially complex scenarios. Scientists believe this may reflect the brain's effort to simulate interpersonal challenges. test responses, or resolve lingering tensions. This could be particularly useful for adapting to new social environments, recovering from emotional upheaval, or preparing for difficult conversations. One theory, known as the threat simulation theory, proposes that dreams evolved to help early humans rehearse responses to dangerous or uncertain situations. In this view, dreaming is a kind of overnight boot camp, a place where the brain trains itself to detect patterns, avoid harm, and make quick decisions. While modern threats may not involve saber-toothed cats, our dream worlds often include social embarrassment, failure, or conflict, the kinds of challenges we navigate daily. Dreams are not just simulations, though. They also seem to facilitate creativity. A brain freed from sensory input and rigid logic can explore new connections, synthesize disparate ideas, and rehearse hypothetical scenarios. Studies have shown that people woken during REM sleep are more likely to generate original ideas than those woken during non-REM stages or who are kept awake altogether. This creative edge is not limited to artists or writers. It can enhance innovation in science, engineering, and everyday problem-solving. In recent years, researchers have taken these insights further by experimenting with targeted memory reactivation. This technique involves pairing new information with a sensory cue, such as a sound or smell, during learning. When the same cue is presented again during sleep, the associated memory can be strengthened. For example, students who studied vocabulary while exposed to a specific sound and then heard that sound during slow wave sleep performed better on tests the next day. These findings suggest that memory enhancement can be guided to some extent by reactivating learning traces in the sleeping brain. However, this is not a limitless power. The brain cannot acquire new information during sleep in the way it does while awake. Playing an audiobook or language tape while you sleep won't make you fluent in Spanish by morning. Sleep is not for raw input. It is for refining what's already been encountered. Trying to cram information into the brain during sleep tends to produce noise, not clarity. Instead, the most effective approach is to learn actively while awake and allow sleep to do the invisible work of reinforcement. This division of labor, waking study and sleeping consolidation, reflects a biological optimization that has evolved over millions of years. Fighting it is both futile and counterproductive. Beyond personal performance, sleep's role in learning has implications for education systems, workplace training, and healthcare. For example, adjusting school start times to align better with adolescent sleep patterns has been shown to improve academic outcomes, reduce absenteeism, and even lower accident rates among teen drivers. Similarly, ensuring that medical residents and night shift workers get sufficient rest can improve performance and reduce errors. Sleep is not just an individual concern. It's a societal resource, and yet it remains undervalued. Many cultures continue to associate late nights with productivity, short sleep with toughness, and fatigue with dedication. These assumptions, though persistent, are biologically flawed. The well-rested brain is not a luxury. It is a requirement for complex thought, sustained attention, and long-term success. The irony is sharp. In our rush to do more, we cut short the very process that makes doing more possible. We schedule early meetings, answer emails past midnight, and drink caffeine to stay alert, all while sacrificing the quiet neurological processes that underpin our effectiveness. It's like polishing a machine constantly without giving it time to cool, repair, or recalibrate. But when we do sleep, truly and deeply, the brain becomes its most diligent student and its most skilled teacher. It reviews, corrects, augments, and integrates. It transforms disjointed moments into stable knowledge, aligns emotions with reason, and turns fleeting impressions into lasting impressions, all while the eyes are closed and the world drifts into silence. In this unseen activity lies the essence of learning, not just to acquire facts, but to know what they mean, how they fit, and how to use them. This is the mind's overnight journey, subtle, silent, and utterly essential. Within the silent landscape of sleep, the human brain performs one of its most astounding feats. It learns without trying. This is not learning in the conventional sense, with flashcards or lectures, but learning at the cellular level. Carried out in the shadowy corridors of the unconscious mind, while the body appears still, the brain becomes a kind of internal workshop where the day's impressions are molded, corrected, and fitted into a broader framework of understanding. At the heart of this process is memory consolidation, which does not merely mean storing information, but integrating it, adjusting, refining, and even rewriting it based on existing structures. New memories, particularly fragile ones, are vulnerable to disruption if they are not stabilized during sleep. That is why people often forget information learned right before bed if they do not sleep properly afterward. The mind requires sleep to protect, stabilize, and contextualize its daily intake of knowledge. The consolidation process is not uniform. The brain handles different types of memories in different ways, often assigning them to specific sleep stages. Declarative memories, like facts and events, benefit most from deep slow-wave sleep, typically found in the first part of the night. Procedural memories, such as learning to play piano or mastering a skateboard trick, are processed in stage 2 and REM sleep, which dominate the later cycles of the night. Each stage has a purpose, and the timing is critical. Shortening or disrupting these cycles can impair learning outcomes even if the total sleep time remains unchanged. A remarkable demonstration of the sleep-memory connection involves the hippocampal replay phenomenon. In studies with rodents trained to run through mazes, researchers recorded patterns of neural activity in the hippocampus as the rats navigated the paths. Then, as the animals slept, those same neural patterns fired again, in the same sequence but at a much faster rate. It was as though the brain was compressing and rehearsing the maze experience, filing it away for future use. This replay is believed to be a cornerstone of memory consolidation and is thought to occur in humans as well. What makes this even more fascinating is that the brain doesn't only replay experiences during sleep. It may also reshuffle them. Memories are not stored as isolated entries in a mental filing cabinet. They are embedded in a vast, interconnected network. During sleep, the brain appears to search for associations between new and old information. It compares, contrasts, and connects, often leading to new insights or understandings upon waking. This is why the solution to a stubborn problem sometimes arrives the morning after you stop thinking about it. Such restructuring is not just theoretical. In experiments involving remote association tests, where participants must find a common link between seemingly unrelated words, people often perform better after sleep. This suggests the brain is not just passively remembering, but actively inventing connections. It operates like a night shift librarian, reshelving thoughts not by subject, but by meaning and emotional relevance. But memory and learning are not solely cognitive. The body's ability to master motor tasks, physical coordination, and reflexive actions also depends heavily on sleep. For instance, in athletes, musicians, and dancers, overnight improvements in skill, precision, and execution are frequently observed. These refinements are thought to occur during REM sleep, when the motor cortex, the area of the brain responsible for movement planning, remains active even while the body is effectively paralyzed. It's a strange paradox. The body is immobilized, while the brain practices motion. This phenomenon might explain why children who are constantly learning new motor skills require significantly more REM sleep than adults. Their growing brains and bodies depend on it. Similarly, in adults learning new physical skills, REM density, a measure of eye movement bursts, has been shown to increase following intensive training. The more effort you spend mastering a skill during the day, the more REM your brain seems to recruit during the night. These observations extend to language learning as well. Acquiring a new language taxes multiple regions of the brain, involving auditory discrimination, grammar rules, memory for vocabulary, and motor coordination for speech. Sleep plays a critical role in solidifying this complex skill set. Functional imaging studies have shown increased activity in language-related brain areas following sleep in language learners, especially after REM-rich nights. Sleep also supports vocabulary acquisition. People exposed to new words and their meanings during the day tend to show better recall and usage after sleeping. Interestingly, even subtle shifts in pronunciation, such as distinguishing between similar-sounding words, are improved after sleep. The brain appears to enhance fine auditory discrimination overnight, contributing to more fluent understanding and speech production. The mechanism behind these gains likely involves a combination of hippocampal replay, synaptic consolidation, and cortical reorganization. It's not just about practicing phrases. It's about making those phrases part of a living neural network. The brain, while you sleep, is embedding meaning into its fabric. On the emotional side, sleep continues to prove indispensable. Stress, trauma, and emotionally intense events create deeply encoded memories. These can interfere with learning and decision-making, unless properly regulated. REM sleep has been shown to reduce emotional intensity while preserving the factual content of such memories. This allows individuals to remember what happened without re-experiencing the psychological pain. In practical terms, sleep acts as an overnight therapy session. Emotional regulation through sleep extends to daily mood and resilience. People who are sleep-deprived often struggle to read facial expressions accurately, respond appropriately to social cues, and maintain impulse control. These effects are not simply the result of tiredness, but reflect impaired communication between the amygdala and the prefrontal cortex. During REM sleep, this neural pathway is reinforced, maintaining emotional balance and social intelligence. Beyond emotional stability, the brain also uses sleep to prepare for future challenges. During dreams, we often simulate situations that have not yet occurred: arguments, exams, performances, or unfamiliar places. These dream rehearsals, though abstract, allow us to confront potential outcomes and refine responses. Whether these are accurate simulations is less important than the emotional preparedness they provide. Like mental fire drills, dreams may help us rehearse how to react when stressors arise. This adaptive simulation extends into social behavior. People who dream more vividly about social interactions tend to perform better on tasks requiring empathy, communication, and perspective-taking. The dreaming brain, it seems, is not just solving math problems or remembering phone numbers. It is preparing you for the complex landscape of human connection. Even nightmares, though unpleasant, might serve a purpose. They could be the brain's way of desensitizing us to fears in a safe environment. A disturbing dream might be a low-risk exposure to something terrifying like falling, drowning, or public failure. In this view, nightmares are not psychological errors, but evolutionary training sessions. Of course, sleep is not always sufficient. The quality, consistency, and timing of sleep all matter. Irregular sleep schedules can disrupt circadian rhythms, leading to decreased memory performance and emotional instability. Likewise, fragmented sleep, caused by noise, discomfort, or disorders like sleep apnea, reduces the effectiveness of memory consolidation and synaptic reorganization. Modern life has introduced new challenges to sleep. Artificial lighting, screen exposure, and erratic work hours interfere with the natural release of melatonin, the hormone that signals to the brain it is time to sleep. Chronic exposure to these disruptions can blunt the brain's ability to enter deep sleep and compromise both learning and emotional regulation. Still, the body is remarkably adaptable. With consistent habits, even small changes, like avoiding screens before bed or keeping a regular sleep-wake schedule, can restore healthy sleep architecture. The brain is always ready to resume its nocturnal work. It just needs the right conditions. Understanding how the brain learns during sleep reveals a larger truth about the human mind. That rest and effort are not opposites, they are partners. For every hour of deliberate study or experience, there must be a corresponding interval of quiet consolidation. Sleep is not a pause in learning. It is learning's secret half. In the darkness behind closed eyes, the brain builds its future. It strengthens what matters, discards what does not, and sketches out new connections in preparation for another day. Without fanfare, it polishes memory, tempers emotion, and sometimes even creates. Beneath the hush of night and behind the veil of dreaming, the brain continues its tireless work, reconciling the old with the new, the known with the unfamiliar. In this nightly symposium, billions of neurons communicate silently. A kind of biochemical parliament passing laws that will govern the next day's behavior, reasoning, and recall. Learning while awake builds the structure, but sleep is the time when the scaffolding is removed and the true form of knowledge is revealed. By now, the notion that sleep reinforces learning might seem intuitive. But what often goes unnoticed is how individual differences in sleep patterns can influence how effectively people learn and remember. Not everyone sleeps the same way, and these variations can have profound consequences. Some people naturally enter deeper stages of slow-wave sleep more easily, while others spend more time in REM. These differences are influenced by genetics, age, stress levels, and even diet, and they subtly shape how well we retain knowledge. Take the example of high performers in cognitive testing. Studies have shown that individuals who exhibit more pronounced sleep spindles during stage 2 sleep tend to perform better on reasoning tasks and fluid intelligence measures. While correlation doesn't mean causation, the pattern is consistent. Across many experiments, sleep spindles, those brief bursts of electrical activity, appear to represent moments when the brain is actively integrating newly learned material with existing memory frameworks. More spindles might mean more integration, and more integration leads to deeper understanding. Age, too, plays a crucial role. As people age, the architecture of their sleep begins to change. Deep, slow-wave sleep becomes more fragmented, and REM periods tend to shorten. This gradual shift contributes to the well-documented decline in memory performance among older adults. However, not all is lost. Techniques such as auditory stimulation, playing soft, pulsing sounds timed to match the brain's slow oscillations, have shown promise in enhancing memory performance in older populations by boosting slow-wave activity during sleep. For younger individuals, particularly children and adolescents, sleep is a vital period of brain development. During adolescence, the prefrontal cortex undergoes rapid maturation, and sleep supports this remodeling by coordinating changes in synaptic strength and structure. Teenagers are often stereotyped as lazy or sleep-obsessed, but their biology demands more rest. Chronic sleep deprivation during this developmental stage doesn't just lead to fatigue, it interferes with emotional regulation, academic performance, and even the establishment of adult personality traits. This relationship between sleep and learning also manifests in disorders. Conditions like insomnia, narcolepsy, and sleep apnea disrupt the brain's ability to complete its learning routines. Sleep apnea, in particular, repeatedly interrupts breathing during sleep, leading to frequent awakenings and preventing the brain from cycling through deeper stages of rest. As a result, individuals with untreated apnea often report memory problems, difficulty concentrating, and mood disturbances, all of which stems from a lack of uninterrupted learning time during the night. Another relevant condition is delayed sleep phase disorder, where individuals naturally fall asleep and wake up later than societal norms permit. This is common among adolescents and young adults and often leads to chronic sleep debt due to early school or work requirements. The mismatch between biological sleep needs and scheduled obligations means that many people are asked to learn without allowing their brains time to cement the previous day's lessons. This misalignment is not just inconvenient, it's educationally inefficient. From another perspective, even mood and anxiety disorders can be traced back to disturbed sleep cycles. In people with depression, REM sleep often begins earlier in the sleep cycle and may last longer than average. This altered structure may reinforce negative thought patterns or impair the emotional processing normally achieved during REM. In anxiety disorders, poor sleep increases the activity of the amygdala and reduces regulation from the prefrontal cortex, making threat perception more intense and harder to control. It's worth noting that not all sleep is equal. The first few hours of the night tend to be dominated by slow-wave sleep, which is optimal for stabilizing declarative memories, such as facts and events. The latter half, especially near dawn, is richer in REM sleep, which favors emotional and procedural learning. Interrupting either phase by going to bed too late or waking too early means sacrificing one part of this learning spectrum. Understanding has led scientists and clinicians to explore strategies for improving sleep in targeted ways. Beyond traditional sleep hygiene, there is growing interest in techniques like transcranial stimulation, which uses mild electrical currents to boost slow-wave activity, and neurofeedback, which trains individuals to modulate their brainwave patterns for better sleep onset and quality. While still experimental, these interventions suggest a future where sleep is not just protected, but optimized for cognitive gain. Technology is also playing an increasingly prominent role in how we understand the relationship between sleep and learning. Consumer wearables can now estimate sleep stages, track interruptions, and provide users with detailed reports about preset reports about their rest patterns. While these devices are not as accurate as lab-based polysomnography, they offer unprecedented insights into sleep behavior at scale. Combined with artificial intelligence, this data can reveal population-level trends, such as how stress from global events affects sleep, or how new routines, like remote work, change our nightly rest. This feedback loop between awareness and behavior is powerful. People who monitor their sleep tend to improve it, whether by adjusting bedtime routines, reducing caffeine intake, or incorporating wind-down activities like reading or meditation. As sleep quality improves, so too does learning, creativity, and emotional resilience. The link is both robust and reversible. Improve one, and you often improve the other. Still, a question persists. Can we hack sleep to learn new material more efficiently? The short answer is no, at least not in the way popular culture sometimes imagines. You cannot absorb a textbook through osmosis while snoring gently on your pillow. Passive exposure to new material during sleep generally does not result in measurable learning gains. The brain requires active attention to form new memories, and that attention is suspended during sleep. However, what can be enhanced is the retention and integration of information learned during the day. With the right timing and cues, memories can be reactivated and strengthened. This is the essence of targeted memory reactivation. In one experiment, subjects learned to associate sounds with visual images. Playing the same sounds during slow-wave sleep triggered reactivation of those visual memories, improving recall performance afterward. This line of research opens new doors to tailored memory consolidation, where specific pieces of information are nudged into stronger retention. Of course, even this enhancement has limits. Overstimulation during sleep can cause arousal, interrupt cycles, and negate the benefits. The brain protects itself from excessive intrusion during sleep for good reason. Dreams, memory consolidation, synaptic pruning, all of it depends on maintaining a relatively undisturbed internal state. The goal is not to pack more into the night, but to allow the brain to perform its natural functions without interference. There's also an ethical dimension to this frontier, as methods for influencing sleep-based learning become more sophisticated. Questions arise about consent, privacy, and the integrity of memory. Could employers or institutions one day attempt to influence employee beliefs or knowledge through sleep-based prompts? While this might sound speculative, the pace of research suggests it's not purely science fiction. Sleep is a vulnerable state, and any attempts to manipulate it must be approached with extreme caution. Still, the vast majority of benefits are personal, quiet, and internal. Improved memory recall, sharper thinking, greater emotional clarity. These are the gifts of sleep, given not through effort but through surrender. The brain, in its nighttime work, does not ask for recognition. It simply asks for the time and space to do what evolution has trained it to do. When we allow it that space, we tap into a source of intelligence far older than language or technology. We connect with a process that has shaped minds since the dawn of consciousness, a process that, in its silent rhythm, continues to refine, update, and sometimes reinvent the self. Beneath the surface of our awareness, the brain does not merely dream. It rehearses, it revisits, replays, reshapes. Like a meticulous editor scanning pages of a manuscript written during waking life, the brain reads through memories with a discerning eye. It chooses what to keep, what to enhance, and what to discard. This nocturnal activity does not occur at random. It follows patterns, rhythms, and cycles that have been refined over countless generations. One of the most important discoveries in modern neuroscience is the role of sleep in shaping what we value and prioritize in memory. Not all memories are created equal. Some fade within minutes, others remain vivid for years. What determines this disparity isn't just the emotional intensity or novelty of the experience. It is also how the brain categorizes and reinforces these memories during sleep. If something matters, if it carries emotional weight, future relevance, or personal meaning, it is more likely to be rehearsed and retained during sleep. This process, often unconscious, is called memory triage. It's the brain's way of handling the flood of information it encounters each day. Imagine walking through a city for the first time. You might see hundreds of faces, hear dozens of voices, read signs, glance into windows, cross streets, avoid obstacles. You can't remember it all, nor should you. During sleep, your brain evaluates which fragments of this sensory overload deserve long-term space. It sifts for value, and that value is not always rational or obvious. In emotional learning, this mechanism becomes especially powerful. Traumatic experiences, for example, are encoded rapidly and deeply. The brain tags these memories with urgency, often ensuring their retention, even at the cost of psychological comfort. Sleep plays a dual role here. It both solidifies the factual aspects of trauma and gradually diminishes the associated emotional charge. This duality allows a person to recall an event without being overwhelmed by it, an adaptive process that supports resilience. However, in cases where this balance is disrupted, as in post-traumatic stress disorder, the memory may be repeatedly replayed in sleep without emotional desensitization. The brain, caught in a loop, cannot reduce the distress signal. The failure of sleep to process emotion correctly becomes a liability. Treatments for PTSD increasingly incorporate sleep therapy or dream rescripting as essential components, reinforcing the idea that what happens during the night profoundly influences how we recover from psychological injury. Emotion, of course, is not limited to trauma. Everyday learning is shaped by how we feel. When something sparks curiosity, embarrassment, joy, or confusion, the brain flags it for special attention. These emotional bookmarks guide the hippocampus in deciding which memories to prioritize. During sleep, this guidance is refined further. Events of the day are re-examined from different angles, with emotional salience often shifting. A comment that seemed harmless during the day may sting in a dream. A worry may dissolve. This reweighting process helps us update our emotional models of the world. The dynamics of this process depend heavily on sleep quality. Even small disruptions can interfere with emotional recalibration. Alcohol, for example, can help people fall asleep faster but suppresses REM sleep, the very stage needed for emotional processing. The result is often poor memory consolidation and a hangover effect, not just of the body, but of the mind. Similarly, sleep deprivation increases amygdala reactivity, making people more prone to anger, fear, and impulsive behavior the following day. But emotion is not the only axis along which sleep shapes memory. There is also abstraction. Sleep allows the brain to extract general rules from specific experiences. In a learning context, this is invaluable. Students may memorize historical dates or scientific terms, but what transforms rote learning into understanding is the recognition of patterns. The ability to say, "Ah, this works like that." That leap from detail to principle is often forged during sleep. Experiments have demonstrated this in surprising ways. In one study, participants learned a grammar-like system with hidden rules. They were not told there were rules. They simply studied word patterns. Those who slept after learning were significantly more likely to intuit the underlying structure. They couldn't explain how they knew, but their performance revealed that something in the sleeping brain had detected order in the chaos. This kind of rule abstraction is essential not only in academics, but in life. The ability to notice cause and effect patterns, understand social dynamics, or generalize lessons from one situation to another. These are hallmarks of adaptive intelligence. And they are, in part, the product of what the brain does at night. The power of abstraction during sleep also explains why creative insights often arrive upon waking. Artists, scientists, and inventors have long reported sudden solutions to complex problems after a night's rest. The classic story of the chemist Kekule dreaming of a snake biting its own tail, leading to his insight about the ring structure of benzene is only one example. What feels like magic is often the result of the brain's nightly synthesis, connecting disparate elements into a coherent whole. The creativity born of sleep is not limited to professionals. Anyone solving problems, whether planning a trip, navigating a relationship, or building a project, can benefit from the brain's background work. The key is to feed the brain with information during the day and then step back. Sleep is where the ingredients are mixed, the dough rises, and new recipes are invented. Another facet of learning that benefits from sleep is spatial memory. This refers to our ability to navigate environments, remember locations, and understand spatial relationships. In experiments using virtual mazes, participants who slept between training and testing sessions navigated more efficiently than those who remained awake. This improvement is believed to result from hippocampal replay, where the brain reactivates and refines spatial pathways during slow-wave sleep. This has real-world implications. Driving a new route, memorizing a building layout, or even learning a dance routine all require spatial mapping. While practicing these skills while awake is essential, sleep polishes the map, clears the dead ends, and strengthens the neural trails that lead from point A to point B. Equally important is the sleep-dependent process of forgetting. While it may seem counterintuitive, forgetting is as essential to learning as remembering. The brain cannot keep everything. It must prioritize and prune. Sleep facilitates this pruning by weakening synapses that are underused or irrelevant. This prevents cognitive overload, reduces noise, and allows important signals to stand out. This forgetting is not accidental, it is strategic. The brain actively deletes information that lacks emotional resonance, practical use, or repeated reinforcement. In doing so, it clears space for more relevant memories and ensures that what we recall is not simply a jumbled archive, but a functional, adaptive set of tools. The complexity of sleep-based learning underscores just how integral rest is to human cognition. Sleep is not downtime. It is work time for the mind. Time to revise, reorder, resolve, and regenerate. To deny sleep is to deny the mind access to its own improvement. To protect sleep is to unlock the brain's full potential. What emerges from this process is not just sharper memory or improved performance. It is something subtler and more powerful. Wisdom? Wisdom is more than knowledge. It is knowledge that has been tested, connected, weighed, and recontextualized. It is the product of experience plus reflection, and sleep is where that reflection occurs most deeply. Across cultures, dreams have often been viewed as sources of insight, prophecy, or revelation. While modern science may not endorse such mystical interpretations, it does suggest that dreaming is a kind of nocturnal thinking, a mode of cognition that operates under different rules but with clear consequences. We wake not only rested, but reorganized. Sleep, then, is the mind's second day, a hidden interval in which the brain completes tasks it cannot finish while distracted by the outside world. In this sense, every night is an opportunity to become smarter, more balanced, and better, prepared for what lies ahead. Night after night, the mind continues its silent apprenticeship. Each cycle of sleep becomes another chapter in a long and invisible textbook written by the brain itself. No ink, no pages, only pulses of electricity, waves of chemistry, and the rhythm of breathing in the dark. Learning, once thought to be the exclusive domain of waking effort, is now understood to unfold even more deeply in the stillness of slumber. The engine of this transformation is repetition, but not repetition in the conscious sense. During waking hours, you might repeat a phrase, a melody, a list of facts. But during sleep, the brain performs a subtler, more targeted form of rehearsal. It selectively reactivates memory traces and integrates them into existing networks. These reactivations do not always follow the order in which experiences occurred. The brain, when sleeping, shuffles time and meaning in order to optimize understanding. Consider the case of language learning. A person studying a new language hears unfamiliar words and strange sentence structures. During the day, the effort lies in memorizing vocabulary and understanding grammar. But at night, the brain works behind the scenes, reactivating fragments of what was learned, replaying phonemes, and even refining accent. Functional MRI scans have shown that regions involved in language processing light up again during sleep, particularly REM. This nocturnal rehearsal leads to smoother pronunciation, faster word retrieval, and more fluent speech over time. This same mechanism applies to emotional vocabulary. When we learn new words to describe feelings, whether in our native tongue or a foreign one, the emotional resonance of those terms is also processed during sleep. Over time, words like bittersweet or wistful become more than abstract definitions. They become emotionally embedded, infused with meaning, shaped by memory and experience. This emotional grounding enhances communication and self-awareness. The dream state often serves as the medium for such integrations. Dreams may appear disorganized, but they frequently pull from linguistic material learned recently. In one study, students learning a new language reported dreams that featured words or phrases in that language. The more vivid the dream, the more likely those words were retained. It's not that dreaming teaches vocabulary, but that it strengthens emotional and associative links, anchoring new knowledge in the subconscious. Beyond language, sleep enhances our ability to make judgments. During waking hours, humans constantly make decisions based on limited information. Some decisions are immediate and instinctual. Others require reflection. Sleep supports both types. It stabilizes the outcomes of past choices, allowing us to better recognize successful strategies, while also refining our gut-level intuition for future decisions. This is particularly important in social environments where split-second judgments about trustworthiness, intention, or danger must be made rapidly. Studies have shown that people who sleep between exposure to complex social scenarios and the testing of their memory tend to remember not only the facts more accurately, but also evaluate the characters involved with greater nuance. They don't just remember what someone said or did. They better understand why. Sleep allows emotional perspective to take root, helping us see others through a wider lens. This adaptive learning is especially important in childhood and adolescence. Young brains are still mapping the social world, figuring out norms, decoding facial expressions, and building the foundation for moral reasoning. Sleep aids in developing empathy, fairness, and impulse control by consolidating lessons from the day's social interactions. A child who has learned to say, "I'm sorry," may understand the mechanics of apology while awake. But the emotional depth of that lesson, its real significance, often solidifies in sleep. Sleep is also where mental models of the self are updated. We do not simply learn about the world. We learn about ourselves, who we are, what we value, where we belong. These self-schemas evolve slowly, influenced by our interactions, goals, and feedback. During sleep, particularly REM, the brain explores these models, testing different versions of reality in dreams. We see ourselves succeed, fail, hesitate, overcome. These simulations are often emotional and symbolic, offering a narrative canvas upon which identity is quietly painted. Adults, too, undergo this nightly revision of self. A person going through a breakup, a career change, or a personal transformation may find their dreams filled with shifting roles and surreal metaphors. While we may wake feeling confused, the underlying work is clear. The brain is experimenting with new definitions of the self. It is exploring what fits and what doesn't, using memory fragments as props in the theater of identity. Memory, emotion, creativity, identity. Sleep touches every layer of our mental architecture. But what happens when the architecture is under construction? In times of stress or trauma, the normal operations of sleep can be disrupted. Cortisol levels rise, circadian rhythms shift, and the ability to enter deep sleep or maintain REM becomes compromised. In these states, learning becomes inefficient. Memories are not consolidated, emotions remain raw, and insight becomes harder to access. Stress not only prevents learning, but distorts it. People under chronic stress may misremember events, draw incorrect conclusions, or develop maladaptive beliefs. This is not a character flaw. It is the result of an overwhelmed brain operating without adequate restoration. In such cases, prioritizing sleep is not indulgence. It is recovery. Sleep rebalances the stress response system, lowers baseline anxiety, and restores the learning potential necessary for problem solving. Interestingly, the effect of sleep on learning can be observed even in dreams that seem disconnected from waking life. Many people dream of fictional characters, imaginary places, or surreal events. These are not nonsense. They are combinations of real emotional states, reorganized in novel forms. A dream about climbing a staircase to nowhere might reflect progress without direction. A dream of being chased may process anxiety not yet verbalized. Even absurd dreams carry kernels of significance, born from the day's raw input and reshaped during the night. This dream processing becomes even more relevant when creativity is involved. Writers, designers, scientists, and inventors often report solutions arriving after dreams. The subconscious mind, freed from logic, allows concepts to combine in unusual ways. The laws of physics may be violated in dreams, but new insights often emerge from this lack of constraint. Artists wake up with metaphors. Engineers wake up with blueprints. The brain, it seems, continues to work long after the conscious mind signs off. This phenomenon, known as incubation, is well documented. When a person focuses intensely on a problem, then steps away and sleeps, the solution often appears effortlessly. Sleep allows competing neural representations to settle, and the strongest or most efficient ones emerge. It is a competition without a referee, and the winner is insight. Yet even this benefit is not automatic. Sleep must be adequate in duration and quality. Fragmented sleep, short sleep, or erratic schedules diminish the consolidation process, just as a rushed editor may miss crucial errors. A restless brain may fail to draw the connections that turn knowledge into understanding. Quantity of sleep matters, but so does continuity and timing. One underestimated aspect of this learning process is dreaming's effect on emotional reconciliation. Consider forgiveness. It is a complex psychological act that requires empathy, memory, emotional distance, and perspective. People rarely reach genuine forgiveness while fully awake and emotionally activated. But sleep, particularly REM sleep, provides a psychological reset. It buffers the intensity of feelings and allows room for alternative interpretations. Someone might go to bed angry and wake with a softer view. This is not magic. It is nocturnal. Processing, in this sense, sleep becomes a mirror of growth. It doesn't erase conflict, but reframes it. It doesn't dictate meaning, but clarifies it. The brain, in sleep, does not forget what matters. It simply removes the static so that what matters can be heard more clearly. As our understanding of sleep deepens, so too does our appreciation of its complexity. What once seemed like a passive state is now recognized as an active and dynamic frontier of human cognition. Every night, we slip into a biologically orchestrated ceremony, one in which the body is still, but the mind is in motion, dancing through memory, emotion, and identity with astonishing grace. Tomorrow's clarity begins tonight. And in the quiet hours ahead, the brain will return to its work, uncelebrated, unnoticed, but indispensable. In the hush between twilight and morning, the brain's deepest miracles unfold, quiet, persistent, and largely invisible. Sleep is not merely a bridge between one day and the next, but the crucible in which the past is processed. The present is refined, and the future is prepared. To sleep is to learn, to heal, to rewire. And as science has gradually pulled back the veil on this nightly ritual, the view is more staggering than anyone expected. Through the lens of sleep, we now understand learning not as a linear acquisition of information, but as a cyclical process. It begins with curiosity and attention during waking hours. It continues through repetition, error, reflection. But the most powerful transformations, the ones that actually change the brain, occur when we're not trying, when we stop, when we close our eyes, when we give the mind permission to do what it has been doing for hundreds of thousands of years. The sleeping brain is, in a sense, the most authentic version of the self. It is untethered from social performance, immune to distractions, and free from immediate demands. In this state, the brain is able to consider everything: who we were, who we are, who we might become. Without the pressure of acting on it, this is where emotional burdens are sorted, where memories are either woven into meaning or gently erased, and where raw learning is transmuted into understanding. The very structure of sleep reflects its complexity. It is not a single state, but a sequence of stages, each performing a different kind of work. Light sleep eases the body into rest. Deep slow-wave sleep supports physical restoration and consolidation. REM sleep, with its vivid dreams and eye movements, strengthens emotion, creativity, motor skills, and narrative integration. These cycles repeat through the night in 90-minute rhythms, a neurochemical symphony that plays while we lie still. To miss sleep is to interrupt this symphony. To compress it, distort it, or skip stages is to rob the brain of its full toolkit. Chronic sleep deprivation doesn't just make us tired. It makes us forgetful, irritable, impulsive, and often unaware of our own deficits. The ability to think clearly, reason ethically, and manage complex information all suffer quietly. Like a library that remains open but stops organizing its books, the brain becomes chaotic, cluttered, and confused. This decline is not a reflection of weakness or laziness. It's biology. Without sleep, the prefrontal cortex, responsible for planning, decision-making, and self-control, becomes sluggish. The hippocampus, our memory registrar, stops filing new information correctly. And the amygdala, the brain's emotional amplifier, overreacts to threats, often inventing them where none exist. Sleep is the antidote, not the luxury. And yet, so many of us treat sleep as negotiable. We trade it for deadlines, screens, or distractions. We compress it, postpone it, or fill it with noise. Even those who manage to sleep the proper number of hours often do so without the conditions that make sleep truly restorative: quiet, darkness, routine. In doing so, we limit the very power that could make our waking hours more effective, insightful, and meaningful. But it doesn't have to be this way. Sleep, unlike so many other cognitive tools, is available to everyone. It does not depend on education, status, or wealth. It only asks for consistency, patience, and trust. Trust that the brain knows what it's doing. Trust that resting is not quitting. Trust that sometimes the best way to solve a problem is to stop thinking about it and let the mind work in peace. The benefits of embracing sleep's role in learning extend beyond individual performance. In education, encouraging sleep-friendly schedules and respecting natural sleep cycles in adolescence can dramatically improve outcomes. In medicine, understanding how sleep influences memory can help in treating conditions like Alzheimer's, where memory disruption and sleep fragmentation are tightly linked. In mental health, reinforcing the link between emotional regulation and REM sleep could guide more effective therapy and intervention. Even in the workplace, recognizing that productivity is not simply a function of hours spent awake could change how we define effort. A well-rested employee makes fewer mistakes, absorbs training more effectively, and recovers faster from setbacks. A society that respects sleep is a society investing in cognitive resilience, emotional stability, and long-term innovation. But perhaps the most profound gift of sleep is philosophical. It reminds us that growth is not always about action, that intelligence is not always about noise, that some of the most important changes in the human brain happen in silence. The kind of silence found only in the deep recesses of night, where memory, emotion, creativity move like currents beneath the surface. So, what happens when we sleep? The answer is everything. Our minds travel through time, revisiting the day, reweaving the past, rehearsing the future. We refine the way we think, how we feel, and even who we are. The tired brain becomes a learning brain, not through force or willpower, but through rest. It reshapes experiences into insight, and insight into wisdom. It connects dots we didn't know were related. It breathes clarity into confusion and resilience into fragility. And the best part? We don't have to direct it. The brain knows. It has known for millennia. It doesn't require reminders or agendas. It simply needs space, quiet, and time. Sleep is not the end of thinking. It is its continuation by other means. So tonight, when the lights dim and the world grows still, consider this. Every hour you rest is another step toward mastering what you've learned, resolving what you felt, and preparing for who you are becoming. Every moment of true sleep is a silent teacher, carving new circuits in the night. Thank you for spending your time with us here at Sleepless Scientist. We hope this journey into the sleeping brain has illuminated just how profoundly rest shapes intelligence, memory, and emotion. If this video gave you something to think about, or maybe something to stop thinking about, we invite you to like the video, subscribe to the channel, and leave a comment telling us where you're tuning in from and what time it is for you right now. And as always, we apologize if this video made you stay up later than intended. That was never our plan, unless your brain just really wanted to learn more. Now, we invite you to relax. Let your eyes grow heavy. Let the information settle. In a few moments, you'll hear calming ambient sounds to help ease your transition into rest. Let your brain take over. Good night.